Assalamualaikum. Today we are going to start article 5 and 6, in which we'll solve definite integrals by substitution method, and then we learn how to find area between two curves. So let's start with substitution formula for definite integrals. And for this we have a theorem number 7, substitution in definite integrals. Now if we have to evaluate an integral a to b f of g of x multiplied by g prime x and with respect to x, then the limits for transformed integral, which is transformed in u by substituting gx is equal to u, will be ga and gb. So this integral will become integral from ga to gb of f of u du. You can prove this yourself. The steps of proof are easy. So let's start an example to understand this technique. So first example, evaluate integral from -1 to 1 3x squared square root of x cubed plus 1. Now here limits for x are -1 and 1. Lower limit is -1 and upper limit is 1. Now in order to solve by substitution method, we'll substitute it x cubed plus 1 equal to u. Like this, u is equal to x cubed plus 1. So we need to transform whole the integrand into u. So by differential we have du is equal to 3x squared dx, and the integral becomes square root of u du. Now how to transform the limits? As we learned in the previous theorem number 7, that the lower limit will become g of a and upper limit will become g of b. Now in this case a is -1 and b is 1. So our gx is x cubed plus 1. So g of a is equal to g of -1, that is u is equal to g of -1, that is which is equal to -1 cube plus 1, and this is equal to 0. We just plugged in x is equal to -1 in this substitution, and that is it. Now for upper limit, replace x by 1 in this substitution. So we have upper limit for u is equal to 2. So transformed integrand with limits is integral from 0 to 2 square root of u du. Now integrate in a usual manner, and you have 4 square root of 2 by 3. Method 2 you can do yourself. Now next example 2. Again we'll solve this method by transforming the limits of integration as well. Square root of pi by 4 to pi by 2 cot theta secant square theta d theta. Now in this case substitution we make is u is equal to cot theta, and its differential du is equal to minus cosecant square theta d theta. Now upper limit is pi by 2 and lower limit is pi by 4 for theta. Now let's see what are the limits for u. So when theta is equal to pi by 4, then u becomes cot pi by 4, which is equal to 1. And when theta is equal to pi by 2, then u is equal to cot pi by 2, which is equal to 0. So limits for u are 1 to 0. Now this becomes u, cot theta is u, and du is equal to minus cosecant square theta d theta. So cosecant square theta d theta becomes minus du, right? So this is equal to negative of the integral from 1 to 0 u du, which is equal to this. Now by usual integration steps and simplification we have found it. Now next question, integral from 0 to pi by 2 sin x cos x over 1 plus sin square x whole cube dx. Now in this case substitution we make as 1 u is equal to 1 plus sin square x. Now the differential du is equal to 2x cos x dx. So this 2x cos x dx will become du, and denominator will become u cube. So we have 1 over u cube du. Now for limits, when x is equal to 0, u is equal to 1 plus sine 0, which is equal to 1. And when x is equal to pi by 2, then u is equal to 1 plus sine square pi by 2, which is equal to 1 plus 1, which is equal to 2. So our lower limit is 1 and upper limit is 2 for u. And the rest is the usual integration, and we'll have 3 by 8. Now there are few results for symmetric functions. If a function is an even function, we already know that function is even, fx is even if f of minus x is equal to f of x, and fx is odd if f of minus x is equal to minus f of x, right? Now keeping this definition in mind, this is the graph of even function and this is the graph of odd function, right? Now theorem 8 gives us two more results, and these are very important. You should remember these results in later applications, for later applications. So let's see what theorem states. Let f be a continuous function on symmetric interval minus a to a, and if f is even, then integral from minus a to a fx dx is equal to 2 times integral from 0 to a fx dx. And if f is odd, then integral from minus a to a fx is equal to 0. Now proof of this theorem is left for you as an exercise, although it is solved in the book. If you have some problem, you can ask me later. And let's understand the geometry of this theorem. In this case, function is an even function, so the area covered under the curve and above x-axis from minus a to 0 is same as area under the curve above x-axis from 0 to a. So we can write this integral minus a to a is equal to 2 times integral from 0 to a. Now in this case, function is an odd function, so this portion is the positive, gives us positive area, and this gives us negative of the area, and similarly this is positive and this is negative. So in total, when we integrate this function minus a to a, its integral will be 0, right? Because area above x-axis covered by the curve and area below x is covered by the curve are same. So when we add both the areas, we will have the value of this integral is 0, right? So area is not 0, as we already know. Area is not equal to 0, but value of this integral will become 0. So this is an example for the application of theorem number 8. Evaluate integral from minus 2 to 2 of x square minus 4x square plus 6 with respect to x. Now see, x4 minus 4x square plus 6 is an even function, because when we replace x by minus x in this function, the function remains unchanged, right? If we replace x by minus x in this term, this will remain x4. Similarly, if we replace x by minus x in this term, this will also remain the same. And this term is actually independent of x, so replacing x by minus x won't affect this. So this whole function will remain same if we replace x by minus x. So this means this function is an even function. Now, using theorem number 8, integral from minus a to a fx dx when fx is an even function is equal to 2 times 0 to a. Now, a in this case is 2, so this integral is equal to 2 times 0 to 2 x square minus 4x plus 6, and after integrating and simplification we have 232 over 15. Now, area between the curves. So if we have upper function fx and lower function gx, this order matters actually while evaluating the area between the curves, upper curve uh, and lower curve. So before finding the area, you should draw the figures so that you can see which curve lies upwards and which curve lies downwards. So this is important to figure out the upper and lower curve while evaluating area between the curves. So if we have upper curve y is equal to fx and lower curve y is equal to gx, and we have to find the area between these two curves from some point A to some point B. So we actually need to find the area bounded by the line x is equal to a, x equal to b, and bounded above by the curve y is equal to fx, and bounded below by the curve y is equal to gx. So if we use Riemann sum to find this area, this is the small rectangular portion of the area, and this area can be evaluated by the formula height multiplied by width. Now height in this case will be f of ck, if this is the point of reference ck, if f of ck minus g of ck, right? So height is f of ck minus g of ck, and width here is delta xk. So this is the area of one triangle. Now adding all such triangles, we'll have approximate area of this region bounded by these curves, and x is equal to a and x is equal to b. Now keeping this in mind, we have definition of area using integral. F and g are continuous such that fx is greater or equal to gx. This means fx is upper curve and gx is the lower curve throughout the integral ab. So this condition must satisfy a throughout the integral. In case in some portion of the interval this does not satisfy, then we'll have to do some manipulations to make it happen. So if f and g are continuous with fx is greater or equal to gx throughout closed interval AB, then the area of the region bounded by the curves y is equal to fx, y is equal to gx from a to b is the integral of f minus g from a to b. That is, an area is equal to integral of fx minus gx from a to b. So let's understand this concept by solving few questions. So first example. Example number 4, find the area of the region enclosed by the parabola y is equal to 2 minus x square and the line y is equal to minus x. So first of all, we draw these two curves. Y is equal to 2 minus x square and y is equal to minus x. Y is equal to minus x is the line, which you can see is shown in yellow color, and y is equal to minus 2x square is the parabola here. So here A and B are not given, so which means we have to find these points ourselves. So if points are not given, area bounded by the curves will be the area which is bounded by the upper curve and the lower curve from the one intersection point to another intersection point. So what we need to do, we have to find the points of intersection of both the curves. For this, equate both the curves, that is, equate the heights so that you can find the value of x where heights are same. So 2 minus x square is equal to minus x. So by solving this, we have x is equal to minus 1 and x is equal to 2. So when x is equal to minus 1, we have y is equal to 1. So this is the point of intersection, and second point of intersection lies at x is equal to 2. So when x is equal to 2, y is equal to minus 2. So these are the points of intersection of both the curves. So we have to find the area between the curves from minus 1 to 2. So by the definition of area between the curves, we have integral from a to b, fx minus gx, as the upper curve minus lower curve, and this is equal to integral from minus 1 to 2, because a here is minus 1 and b here is 2, and our upper curve is 2 minus x square, so fx is 2 minus x square, and our lower curve gx is y is equal to minus x. So just replace gx by minus x and then integrate from minus 1 to 2, and we have 9 over 2. So this is the area between these two curves. Now example number 5. Find area of the region in the first quadrant that is bounded above by y is equal to square root of x and below by the x-axis and the line y is equal to x minus 2. So this area has basically two parts. One part bounded above by y is equal to square root of x, that is this curve, and bounded below by x-axis, that is y is equal to 0. So first part is shown in this figure by A in mustard color, and second part B, which is bounded above by y is equal to square root of x and bounded below by y is equal to x minus 2, and uh, from x is equal to 2 to x is equal to 4, and this x is equal to 4 is obtained by finding the point of intersection of these two curves, right? So let's try and find out, and what we need to do, we'll find area of this portion, and then we'll find area of this portion, and then in order to find a total area, we'll add them up. So let's see. So this is the first part for x 0 to 2, that is x lies between 0 to 2, and this is the area shown in this region. Fx minus gx, fx is square root of x and gx is 0 in this case, so fx minus gx is square root of x minus x, which is square root of x. And for the region from 2 to 4, x lies between 2 to 4, fx minus gx is equal to square root of x minus x minus 2, which is equal to square root of x minus x plus 2, and let's integrate both of the function in respective intervals. So total area is integral from 0 to 2 square root of x plus integral from 2 to 4. This is area of region A and this is area of region B, and rest is the matter of simplification, and we have 10 over 3 is the answer.